Hello, everybody. Welcome. My name is Adrian Broz. I'm glad that you're all here today. Today, I'm going to be talking to you about the potential preservation of biosignatures in some of Earth's earliest soils, also known as paleosols. And so on the menu for today, we're broadly discussing two research questions. So for one, are there signatures of life preserved in Earth's earliest soils? And second, are these soils rich in sulfur like rocks on Mars? And so we're going to take a series of two different field studies. We're going to first look at Archean 3 billion-year-old acid sulfate paleosol from Australia and the feral quartzite. And then we'll move to an Archean acid sulfate paleosol from Greenland that appears to be about 3.7 billion years old from the Isua supercrustal belt. So more broadly, and to take a step back, why are we doing this work? So for one, we want to understand, should putative paleosols on Mars be targeted for future exploration, whether that's for biosignature investigation or for Mars sample return? And specifically, we want to understand, well, do these Archean age paleosols from Earth preserve detectable organic carbon? And second, is the preservation of organic carbon related to the sulfur content of paleosols? So to begin, also to take a step back, what is a paleosol? Well, it is a buried, fossilized surface environment or soil, which is now lithified into a sedimentary rock. And most commonly, paleosols form from rapid burial, whether that be from volcanoes, landslides, dust storms, sedimentation from flooding, ash and tuff deposits, which cap and bury the soil. We can see here sort of an Anthropocene on the left version of a paleosol being created in real time by a lava flow on the Big Island of Hawaii, and then sort of on the right a paleo version of this burial event, which is burying the soil. This is on the right a Miocene age intrabasaltic paleosol, this red layer here, and that has been buried by flood basalts from the Columbia River basalt. So how do we recognize paleosols in the field? Well, there's a couple different ways morphologically. Most often they have what's called a sharp top, which is the burial layer or the cap. And this most often in the case of sedimentation from flooding as the burial mechanism leads to cross bedding, which is then capping. You can see the underlying bed here, this destruction of bedding, which is characteristic of bioturbation and pedoturbation during soil development. It just kind of destroys that original bedding or relic bedding. And so the fossil record of soils is on Earth, from the Archean to the Holocene and everywhere in between. On the left here, we can see a Pleistocene age buried mollusol here. This black layer, which is buried by approximately 2 or 3 meters of loess. And on the right, we can see a potential paleosol from Greenland. We'll be looking a little bit more on this one in this talk, that has a burial cap up here and then a series of diffuse horizons, which are a common characteristic of soils. And our rationale for studying paleosols on Earth that are really old is that Archean age ones from about 2.6 to 2.7 billion years preserve biogenic organic carbon probably derived from cyanobacterial mats. Second, there's mounting evidence of widespread surface weathering leading to pedogenic weathering on Mars billions of years ago. And third, paleosols have recently been named a high priority site for biosignature detection and Mars sample return. And so why paleosols on Mars? Well, based on all the mineralogical and remote sensing evidence, it's possible that a Gale crater Curiosity could encounter a paleosol. Similarly, at the Noachian age Jezero crater, this paleolake with an extensive delta system where Perseverance landed last February, there's on the western delta and sort of the northern fan, there's these ubiquitous and widespread dioctahedral aluminum clay and silica deposits that are associated with these point bar settings, which suggest surface weathering or the presence of paleosols. And we know so much about the surface of Mars because of our orbital remote sensing, primarily in the visible and near infrared range, which across Noachian age terrains on Mars has really detected in thousands of locations dioctahedral aluminum and iron magnesium clays that are associated with formation in pedogenic or soil settings. And when you overlay stratigraphy on top of these mineralogical maps by overlaying the mineralogy with a digital elevation model, we can see that there's this pedogenic-like stratigraphy where aluminum clays overlie iron and magnesium clays. And they're all Noachian in age, 3.7 billion years and older. So we know so much about the surface of Mars in situ because of the sample analysis of Mars SAM instrument, which the goal is to assess the passivability and isotopic composition of the surface in the atmosphere. And this is one of the instruments we use to characterize the Archean paleosols. So we'll get into talking about it in our methods in a minute. But it operates largely in two modes, SAM EGA mode, which detects bulk gases, and SAM GCMS mode, which detects through molecular separation individual organic molecules. But here we're only going to run it in SAM EGA mode to look at our Archean paleosols for the first time. And so with this instrument, SAM, onboard Curiosity, organic carbon has been detected in association with sulfur. So either through sulfurization reactions, which cross-link and stabilize different forms of organic carbon, which in this case look to be kerogen-like, up to 10 parts per million, or it's locked up in the crystal structure, in the crystal lattice of sulfate minerals like gypsum, basanite, and pyrite. And so it's thought that sulfur, through either sulfurization or reactions with mineral surfaces or locking in sulfate minerals, sulfur is aided in the preservation of organic matter on Mars for billions of years. And so on Earth, we see evidence both in geochemistry and morphology of ancient rocks and sediments that we might have had some undergoing acid sulfate weathering on the surface of early Earth, like on Mars. And so for this work, we will first compile the previously published observations of Archean paleosols, including total organic carbon and bulk geochemistry. We then performed a SAM EGA analysis on a Greenland paleosol to look at the influence of mineralogy on total organic carbon. And then we related in the Australian paleosol total organic carbon with a number of pyrite framboids. So that's sort of a metric of the sulfate content or the ancient sulfur content of these soils. So the SAM EGA instrument works like this. It heats our sample up in an oven here and here to about 900 degrees centigrade, and the sample decomposes into volatile gases. Those gases get sucked into a mass spectrometer and identified based on their mass charge ratio. This constrains mineralogy and carbon content of the samples, and without the need for any harsh acid pretreatment to remove any inorganic carbonates. So here's the Greenland soil. It's a potential 3.7 billion year old acid sulfate paleosol based on its geochemistry and its morphology. And so we took this sample and ground it down and subjected it to total organic carbon and isotopic del 13C analysis, so stable carbon isotopes. And we can see here with depth, there's this marked increase, both in total organic carbon, which was remarkably high, up to 1.6 weight%, and del 13C ranging between 24 to 27 per mil, with slight Rayleigh distillation at the surface, which is a common feature in soils, modern soils, that's attributed to the decomposition of organic matter in the surface enriched horizons. And so we can see some really interesting trends here with our evolved gas analysis. So on the y-axis is CO2 ion current and SO2 ion current here in the yellow and red respectively. On the x-axis is temperature. And on this second y-axis, we can see we have heat flow, the dotted line here. So this is telling us whether we have an endothermic reaction or an exothermic reaction. And so at around 400 C, we see this big burst of CO2, this big release of probably organic carbon, which is accompanied by a slight sulfur SO2 peak here. But most notably, we also have a potentially what looks to be a kerogen peak. So a much higher temperature, much more thermally stable peak, accompanied by a large exothermic heat release here. And this is characteristic of organic carbon decomposition. So this are either from mineral-associated carbon, kerogen compounds, or as we can see here, tailing off with a CO2 release at really high temperature, around 900 degrees centigrade, organosulfur compounds. And so, yeah, we have trying to still figure out what this all means, but it looks to be like there is potentially some preserved organosulfur compounds in these ancient soils. And so we're not sure what the source of those is at this point, so we can't rule them as being biogenic or abiogenic. But moving on now to the second soil, shifting gears a little bit towards Australia, we're looking now at a 3.0 potential acid sulfate paleosol from the feral quartzite in the Pilbara Craton in Australia. And morphologically, these profiles look really similar to soil profiles in modern times, especially acid sulfate soils. And so we measured here on the right total organic carbon as a function of depth. And we previous work has shown the presence through thin sections that there are these carbonaceous microfossils, which have been envisaged to be things like a terrestrial community of actinobacteria and purple sulfur bacteria, and even possibly methanogenic archaea. Also in these samples, there is framboidal pyrite in abundance. So this is the iron sulfate mineral. It's framboidal, which is sort of resembles the drupes of a raspberry. It's really elegant crystal form. And so we related the number of opaque pyrite framboids in each sample with the total organic carbon content of each sample. And we found a significant relationship across 10 or 11 samples that the more pyrite framboids we have, generally the more organic carbon. We did have this outlier, which I did choose to include because it was the sample with both the highest organic carbon content and the most framboids. So this suggests that sulfur is in some way or shape or form related to the preservation of organic carbon in these soils. So that's what we're at right now. This is sort of preliminary and ongoing research, so we can't draw any conclusions as to whether these ancient soils contain biogenic organic carbon, because there are many ways that abiotic organic carbon can be formed. We also need to know, like if there's any modern contamination, which we haven't done yet. And so radiocarbon dating of these samples would be a way to rule out any recent or modern contamination from stuff less than about 50,000 years old. So that's all I got. Thank you guys very much for your time. And yeah, I appreciate it.